88. Sorry about not posting day 87 till this morning. So tomorrow in class, if you could show me both day 87 and day 88, that would be awesome. Today we're looking at the last kind of big topic in this unit. Okay, so we're looking at these regions trapped between two curves. Now it's going to be the base of a solid, right? And we're going to look today at cross sections that are perpendicular. That perp means perpendicular, perpendicular to the x-axis. So once again, this is kind of hard to illustrate, but I'm going to try my best to illustrate it. Here's what we have. So let's say we have an xy axis here. I'm going to try and illustrate what this looks like. And once we kind of get the idea of what this looks like, we don't have to do quite all this sketching. But here's what we're going to have. We have a function f of x, and we have a function like this, g of x. Okay, so once again, we know how to do a lot with this, right? I can find the area of R. I'll call this region, I'll call the region S. So there our region is called S. I could find the area of S, right? To find just to recap here, I would need to know this intersection point and this intersection point. We'll call them A and B. I could find the area of S by doing the integral from A to B of f of x minus g of x. That would give me the area of S. I could take that region S and I could revolve it around the x-axis. If I did that, my volume would be pi times the integral from A to B of f of x squared minus g of x squared. Or I can take that region S and revolve it around a different horizontal line, maybe like y equals -3, somewhere down here. If I revolved it around y equals -3, then my big radius would be f of x plus 3. So my volume would be pi integral A to B of f of x plus 3 squared minus quantity g of x plus 3 squared. Or I can revolve it around a line up here, maybe y equals 10. Then I'd have volume equals pi integral A to B of 10 minus g squared for my big R squared and 10 minus f squared for my little r squared. Okay? Or I could take this thing and revolve it around the y-axis, right? So we can do lots of different things. Today, we're going to say that this region is the base of a solid whose cross sections perpendicular to the x-axis are squares. Okay? So this is the base of a solid, and so that solid is coming out straight at you through the screen. To get like a better idea of that, I'm just going to sketch this at an angle. So here's what we're going to have. This is going to be the y-axis. This is going to be the x-axis. Okay. F of x is going to look like this. G of x is going to look like this. Okay. So here is A, here is B. Okay. So what's happening here is this region S here is the base of the solid. And it's what we're going to say is the cross sections are squares. Cross sections perpendicular to x-axis. Okay? So here again, here's the x-axis. Perpendicular to the x-axis are squares. So what we have here is these cross sections are going to be squares. Well, what we know is we have this distance here. We have a square. Out here, the squares are going to be a little bit bigger. Okay? Here, the squares are really small. So what we have is this three-dimensional shape. Well, it's we have this three-dimensional shape popping out at us, whose the cross sections are all squares. Okay? And what we want to do is find the volume of this solid. Okay? So imagine these things popping out at you as squares. Okay? Well, this whole unit, sometimes we'll have squares, sometimes we'll have right triangles, sometimes we'll have semicircles. Could have a lot of different things. Okay? But what we want to do here is we want to figure out what is this thing going to, how are we going to find the volume of this? Okay? Well, what I want you to do is think about pulling out one of these squares. Okay? And once again, we're going to have a thickness of dx. Okay? Now we know that for squares, all sides are the same length. So what we want to do is we want to understand that this distance right here is the same distance that it goes up, over, and down. Okay? So the question is, how do I come up with that distance? What is the length of that line? Well, once again, this line is a length f. This line is a length g. So the length of this black line is always going to be f of x minus g of x. Okay? So here's my square that I'm looking at. I have, square prism here. And again, I'm just going to look at one of these and kind of figure it out from there. I know that this length right here is f of x minus g of x. Whatever shape we're using, it doesn't matter what the shape, this length right here is always going to be f of x minus g of x. But the height of this thing, since it's a square, has to also be f of x minus g of x. And its thickness is dx. So what I'm going to do is I'm going to write an integral. This is going to be just like the washer method, kind of, right? I'm going to write an integral that's going to sum up all of the areas of all of those squares. Okay? So what I want to do is find the volume of one square, and then I'm going to integrate all of those from A to B. So again, what is the volume of this shape? Well, I'm just going to do the area of the square times the thickness dx. The area of the square is f of x minus g of x squared. That's the area of the face. Multiplying by the depth dx will give me the volume of that cube. But I want to sum up the volume of all of those little cubes from A all the way to B. So to answer this question, our volume is going to be the integral from A to B Right? I'm going left to right because my cross sections are perpendicular to the x-axis. I'm going to do the integral from a to b of the volume right here. So it's going to be f of x minus g of x quantity squared dx. Okay? One thing I want you to note, did we have any circles here? Or semicircles? No. So notice how there's no pi in this equation. Whenever we do washer method or disk method, we always have pi. And we do big R squared minus little r squared. Okay? And notice with the washer method, it was pi big R squared minus little r squared. That's different than f of x minus g of x, that whole quantity squared. So we want to be very precise when we write these. This isn't the same as f squared minus g squared. It's got to be quantity f minus g squared. Okay? Now let's think about this for a different shape. Okay, what if I had a similar scenario? Here's my f. Here's my g. Now what if I told you the cross sections, right? This region here is the base of a solid, and now the cross sections are isosceles right triangles with leg in the plane. Okay? Well, how would we do that? Well, again, let's just take a look at one cross section. It's an isosceles right triangle with a leg in the plane. Okay? And again, that triangle is popping out at you, right? It's coming straight up at you. But we know it's an isosceles right triangle. And we know that it's the leg in the plane, not the hypotenuse in the plane. Okay? So, once again, I just want to find, right? I'm just going to sketch this here. We don't have to do these sketches all the time. So here is our isosceles triangle. I pulled it out, okay? But once again, what we have is this is the most important dimension right here. That dimension right there is always the difference of f and g. This length is f of x minus g of x. Top minus bottom, okay? So this is going to translate to right here. This length right here is f of x minus g of x. But since this thing is isosceles, that means the height of the triangle is also f of x minus g of x. And again, I have this thickness dx. So the volume of one shape here is going to be the area of the triangle times the thickness dx. Well, what do I know about a triangle? Well, I know it's base times height divided by 2. Or you can think of it as 1/2 base times height. But notice, since this is isosceles, the base and the height are both f of x minus g of x. So my volume is 1/2, because it's a triangle, not a square, base times height. Well, that's going to be f of x minus g of x times f of x minus g of x. So I'm just going to write it as half f of x minus g of x, quantity squared, dx gives me the thickness. So if I wanted an integral to represent this, again, here's my a, here's my b, I'm going to say the volume is the sum of all of those. So it's going to be the integral from a to b. I'll put the half out front because it's a coefficient. And it's f of x minus g of x quantity squared dx. This would be my answer. Now, once again, These tend to show up on the calculator section, so we just plug them in and do it on our calculator, or on the no calculator section, where all we have to do is write but not evaluate. If we did have to evaluate it, hopefully it wouldn't be too tough of an evaluation. Okay. Now this can work for any shape that they describe. Now shapes I've seen are squares, rectangles, right triangles. I've seen semicircles. Okay, because we're getting kind of long in this video here, I'm going to stop there, but I just want you to know that it could be any shape. But what the most important thing is right here. This distance is always f of x minus g of x. So that gives you at least one aspect of the shape, and then you just have to use your mind to figure out the remaining volume of that slice. Okay, that's a little difficult, I understand, but we'll get some time to practice tomorrow. Those of you going to robotics, have a great competition, do really, really well. Swing by, check me out in the morning, and see if I can get you the homework for today. Practice it, check the keys, and that's it. I'll talk to you guys tomorrow. 2 chains. Bye.